Next, we'll find the pH of a weak acid solution in cases where the X's small approximation doesn't work. Find the pH of a 0.1 molar HClO2 hypochlorous acid solution. Here we have the dissociation equation for hypochlorous acid. That's hypochlorous acid plus water yields H3O plus the hypochlorite ion. And we set up our ice table: initial, change, and equilibrium. So initially we have 0.1 molar of the acid, essentially none of the hydronium and none of the chlorite ion. And our change will be represented by losing X of the acid, gaining X of the hydronium, and gaining X of the hypochlorite. At equilibrium, we have 0.100 minus X of the acid, X of the hydronium, and X of the hypochlorite ion. We set our products over reactants equal to the Ka. So here's our Ka expression, and that's equal to X squared over 0.1 minus X, because X was the acid and also the anion concentration, so that gives us X times X, which is X squared, over 0.100 minus X. If we assume X is small, then we can eliminate it on the bottom where we're subtracting it. We never eliminate it where we're multiplying, okay? And that gives us 0.011 equals X squared over 0.100. Notice the Ka is relatively large here. It's on the order of 10 to minus 2. That's a very large Ka, and we probably shouldn't even have made this approximation. But anyway, solving for X, we take the square root of both sides and we get 0.033. Now when we check our X's small approximation, that's what we subtracted divided by what we subtracted it from. So that's 0.033 divided by 0.1 times 100. We get 33%. So our X's small approximation is invalid. So we need to go back and rework our K expression, leaving the X in. Okay, so how we do that is we just set our equilibrium expression up again, set it equal to the Ka, and we solve for X. How do we do that? Well, we get a quadratic. We're going to get it into the form of the quadratic equation. Remember, it's ax squared plus bx plus c equals 0. And we use the quadratic formula where x is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. So that gives us minus 0.011 plus or minus the square root of 0.011 squared minus 4 times 1 times negative 0.0011. Okay, that's our c. And then all over 2 times a, which is 1. And so that gives us X being negative 0.039 or positive 0.028. Since we can't have negative concentrations, that means our hydronium ion concentration was equal to X, which was equal to 0.028. So we're not done yet. We have to use that to calculate our pH. If X was equal to the hydronium ion concentration, which is equal to 0.028, then our pH is the negative log of that, which gives us the negative log of 0.028, which is 1.55. So our pH of this solution is 1.55. The Ka, if we can recalculate, we can plug in the values for X and the initial and the acid concentration at equilibrium, and we get 0.011, which is equal to the K that we used. So therefore we can conclude that we got the correct answer for X and therefore the correct answer for our pH.